We trust science to give us clear answers, especially when it comes to something as important as our health. But what happens when the science itself is flawed, right from the very start? Today, we're going to pull back the curtain on eye research and look at the hidden biases that can make a study seem perfect, but actually lead to totally wrong conclusions. Let's jump in. So, that's the big question, right? And maybe surprisingly, the answer is a big, fat yes. A study can tick all the boxes, follow all the scientific rules, and still be flat out wrong. And the reason for that usually boils down to this one sneaky, powerful concept: bias. Getting a handle on bias is really the key to seeing past the headlines and figuring this stuff out for yourself. Okay, so what is bias really? Well, the best way to think about it is like you're taking a picture. A random error, that's kind of like a single smudge on your camera lens. It might mess up one photo, but that's it. Bias, on the other hand, is like having a warped lens. Every single picture you take is going to be distorted in the exact same way. It's a predictable, systematic error that's always pushing the results away from the actual truth. So, where does this whole problem even start? Well, a lot of the time it happens right at the beginning of a study with a really simple question: who are we actually going to study? This is where some of the first and honestly biggest flaws can sneak in. And that brings us to our very first red flag: selection bias. This is what happens when the group of people you pick for your study doesn't really look like the larger group you're trying to learn about. Right from the get-go, your sample is already skewed. Check this out. It's a perfect example. Back in 2008, a survey in an optometry journal asked its readers if they thought private practice was better than corporate practice. Now, here's the catch. The readers got to choose if they wanted to respond or not. This is just a classic case of self-selection bias. I mean, think about it. Who's the most likely to take the time to answer a survey like that? Probably someone who feels really, really strongly about it, one way or the other. So the results don't really tell you what all optometrists think, just what the most passionate ones do. And you see this kind of bias popping up everywhere in eye research. Say you're studying myopia, but you only recruit kids from a specialty clinic. Well, your data is going to be packed with severe cases. Or if you're studying how glaucoma gets worse over time, but the patients with the most advanced disease drop out of your study, your results are going to make the disease look way less aggressive than it really is. It's a constant battle. Now, there's this really interesting specific type of selection bias called spectrum bias. And it's a huge deal when we're trying to figure out how good a new diagnostic test actually is. And this right here illustrates the problem so well. Over on the left, you've got the ideal lab scenario. You test a group of very, very sick patients against a group of perfectly healthy people. Of course the test is going to look amazing. The two groups couldn't be more different. But the image on the right, well, that's the messy reality of a clinic. There's a huge overlap between people who are healthy, kind of sick, and very sick. So a test that looked like a miracle in the lab might actually not perform so well in the real world with real patients. Okay, so we've established that picking the right group of people is absolutely crucial. But even if you get the perfect sample, you can still end up with wonky results. The next place bias can wiggle its way in is in the how you actually go about collecting your information. And this brings us to red flag number 3, measurement bias. This is any kind of systematic error that happens during the data collection part. It basically means the information you're gathering is consistently off base from the very beginning. This is such a simple, perfect example. Look at that bad question. How often do your eyes itch and burn? I mean, what if your eyes itch all the time, but they never burn? How are you even supposed to answer that? It's impossible to answer accurately. Researchers sometimes call this a double-barreled question, but look how simple the fix is. Just split it into 2 clear, separate questions, and suddenly you're getting data that actually means something. And this kind of bias can show up in a few different ways. You've got instrument bias, where the tool itself is the problem, like using a machine that tends to overestimate nearsightedness in kids. Then there's observer bias, where a researcher's own expectations can actually influence the results. It might not even be conscious. That's why the best studies are blinded, so the person doing the measuring has no idea who got the real treatment. And then there's recall bias, which is a big one because, let's be honest, human memory is not a perfect recording device. Asking someone to remember exactly how much screen time they had 6 months ago, yeah, that's just asking for bad data. All right, so we've seen how bias can mess with who we study and how we study them, but the story's not over. A study can be perfectly designed, perfectly run, and the results can still get twisted by what happens after all the data's collected. and this is a huge one, often called publication bias or the file drawer problem. It's based on a really simple but powerful fact. Not all research gets published. Some studies, especially those with certain kinds of results, are way more likely to see the light of day, while others just get quietly tucked away in a file drawer, never to be seen again.
So what's the big deal? Well, this chart says it all. Journals, researchers, everybody gets more excited about studies with positive results. A new drug that works, a new treatment that's effective. A study that finds, well, that the new drug didn't work, those are way less likely to get published. This creates a public record of science that's totally skewed toward positive findings, which can make new treatments look way more effective than they actually are.
And finally, even when a study does get published, there's one last little trap we have to watch out for. We'll call it interpretation bias, but a better word for it is just spin. This is when the exciting conclusions in the study summary don't quite line up with the actual data. This quote from Ophthalmology is just a perfect example. A study might find a change in the thickness of the retina that is statistically significant. All that means is that the result probably isn't due to random chance. But the change is only 2 or 3 micrometers. That is unbelievably tiny, and it has zero effect on a person's vision. But the authors might spin this as a huge deal, a major finding, when in reality, it's clinically meaningless. Okay, wow, we have gone through a lot of potential problems, and it might seem a little bit discouraging. But the point here isn't to make you throw up your hands and dismiss all research. The goal is to give you the tools you need to become a sharper, more critical, and more informed reader. So here it is, your very own personal bias detector. The next time you come across a study, just run it through this quick checklist. Number 1, population. Does this group of people actually look like me or my patients? 2, measurement. How did they measure things? Was it objective and rigorous? 3, controls. Did they account for other things, what researchers call confounders, that might explain the results? 4, magnitude. How big was the effect they found? Was it big enough to actually matter in the real world? And finally, 5, transparency. Who paid for all this? Just asking these simple questions can totally change the way you see a scientific claim. Because at the end of the day, here's what it all comes down to. The existence of bias doesn't automatically make a study bad. But unrecognized bias? That's dangerous because it leads us to the wrong conclusions. Your single best defense against being misled is simply being aware that these things exist in the first place. So we'll leave you with that thought. You basically have a new, corrected lens for looking at the world of research. The next time you see a big headline about a medical breakthrough or some surprising finding, what are the questions you're going to ask? Thanks for tuning in.